All right, I'm going to do at least one more of these because I feel like you need something a little unusual. And this will allow us to demonstrate and talk about something a bit unusual, a bit more esoteric. And so the next one I'm going to talk about is NO2. And you'll see why this is a bit unusual in just a little bit. I want to actually have you see it, experience it, try to come up with your own conclusions, and then I will feed you, answers. So much less fun and interesting, but whatever. All right, so nitrogen, again, where do we start? Well, we always are going to start with number of valence electrons. So nitrogen has 5 valence electrons. All right, oxygen, we go down here, group 6, 6 valence electrons for each oxygen. Now there are 2 oxygens. That means that is times 2 for 12. All right, you will notice here that we got a bit of a issue here. It's kind of a weird thing. So 2 times 6 is 12, plus 5, that is 17. So you have an odd number, 17 electrons. Wait, don't we want things like octets? So we can never actually fill up all of our octets, can we? Because an odd number can never fill up even numbers. Ooh, we got a bit of an interesting thing. This is actually referred to as a free radical. It's going to have one spot empty. So it's going to have an empty spot that it could accept an electron. And as you can probably imagine, this tends to be very reactive. Free radicals tend to be quite reactive. This right here is one of the components of what's referred to as NOx, and that is the photochemical smog that you see in cities. This is actually quite bad for you. So that right there is NO2. This is a component of that brown smog you see in like LA and stuff, and Beijing. All right, now that's NO2. We have 17 electrons, so the next thing we have to do is figure out what's going to be in the middle. And so we see nitrogen and oxygen. Well, nitrogen has the most electrons it needs to be noble-like. So we will put nitrogen in the middle. Again, we always put single bonds first. We put what needs to connect to, which are the oxygens. Very good. So we have our little skeleton we can work off of. We have currently used 2 4 electrons. Remember, each bond is 2 electrons. So that leaves us with 13 electrons remaining. All right, now, the next thing we do, well, it's always the same setup, the same procedure over and over. And so we need to distribute these 13 electrons. All right, so we distribute the 13 electrons. We look at oxygen. Remember, when we distribute these, we're always going to do it on the surrounding atoms, not the central atom. And so we have 2 electrons on this oxygen right now. That means that needs another 6 electrons. So we put 3 sets of lone pairs, which is 6 electrons. All right, this oxygen right here has a bond to it, so it needs, again, another 6 electrons. All right. Okay, and so we have accounted for now 6 and 6. That would be 12 electrons. So that's going to be minus 12. My goodness, I'm terrible at writing with this. That leaves us with 1 electron we have not accounted for. And so we need to put that now. It can't go on either of these. They're full. So that can only go on the center. And so we will put that on the center. There you go. We have put that 1 electron on the center, and now we have accounted for all of our electrons. Okay. The next thing we have to do is we need to check and see if everything's full. So the oxygen here, that's full. That has a full octet. This oxygen has a full octet as well. This nitrogen, though, it is not full. It has 2, 4, 5 electrons. It should have 8, just like the oxygens, but it doesn't. And so it is not full yet. we need to move some of these lone pairs here into double bonds. Well, we can't get more than 8 electrons. Remember, that's full. So once we have 8 electrons on the period 2 stuff, that is full. It can't go any higher. So that means we can't actually get up to 8 electrons, but we can get as close as possible. That means we can move one of these lone pairs in to a bond. And so we move that into a bond. I'm going to go and erase that before I talk about more. All right, so we moved that lone pair into a bond. That means we now have 2, 4, 6, 7 electrons on the nitrogen. We can't move another lone pair in because that would give us 9, which is higher than the 8. That's the maximum that we can fit on that nitrogen. So we've gotten as close as we can. This is why it's referred to as a free radical. It's going to have an unpaired electron, which it can rip off of other stuff that it happens to collide with. And so this is quite reactive, yes. Now, that right there is a correct structure for NO2. That is fine, perfect, congratulations. We have completed a Lewis structure now. You will have noticed, though, that we could have done it the opposite way, where instead of taking the lone pair off of the right side, we could have taken it off of the left side instead, like so. And that would have given us this, where we have a double bond on the left instead of the right. Well, which of these is correct? They both are. Really, what we're looking at here is a case of an imperfect two-dimensional system misrepresenting. Okay? So what we're really doing is that left and right, that's an entirely arbitrary assignment. It really doesn't matter. What's really going on here is these are what's called resonance structures. Okay? And that means they would normally be joined by a double arrow like so, which means that they are both correct, or they are both slightly wrong. To truly represent the structure of NO2, you need to look at both of these structures. So in reality, these single and double bonds, they're the same. They're both like a 1.5 bond. They're both halfway between single and double bonds. They exchange that electron density freely between these two. They're the same length. They're the same bonds. Okay? They're the exact same type of bond. There is not a single and double bond. Okay? They're like 1.5s. The best representation and the one that's most famous of this would be benzene, which has a resonance structure and which is all 1.5 bonds around the entire ring, which, if you remember from previous drawings you've seen of benzene, is a 6-member ring like so with a circle in the middle. And that represents all the bonds are the same. They're all 1.5-ish bonds. Okay? All right, very good. We got some resonance structures in there. We got some free radicals, and we, again, hopefully you're drawing along with this. You got to practice your Lewis structures. Really, the only way to master Lewis structures is just practice, practice, practice. Do them over and over. Okay? You got to do them yourself. You can't just copy what other people have done. Now, I promised before I was going to talk about the quick way of doing these things. The quick way is once you've done enough of these, you're going to have pattern recognition. What do I mean about pattern recognition? Well, remember where I talked about all of the groups, the atoms in a group, or the elements in a group? They are going to bond the same. They're going to do the same things. That means if you get a H2O versus an H2S, they're going to do the same things. You're going to have the exact same stuff here. The only difference is one of them will have an oxygen in the middle, one of them will have a sulfur. So for example, if I have PO2 here, I know that PO2, nitrogen, and phosphorus are in the same group. And so PO2 is going to look just like this. And I can just put a P here instead. There you go. Congratulations. You've done it. So when you look at atoms that are in the same group and you've seen it before, you can just write it out. It becomes very, very easy, very obvious. Okay? The next one I'm going to do, I'll do one more, and that will be an extended octet.